We're going to finish off our current electricity unit with capacitors circuits. And I'm going to draw a couple here. So I could have capacitors like this in series, or I could have capacitors like this in parallel. Okay, and we have to figure out the rules. The first thing we're going to say is that this capacitors are open. And once they're charged, current stops. Okay, there's a gap in these capacitors, and current can't flow across that gap once they're charged, and they take milliseconds to charge, so we can pretty much say there's not going to be any current for those. We're going to use this rule, Q equals CV. We had that in our equation, our static electricity unit. Instead of V equals IR, like we do with the resistor circuits, we're going to use Q equals CV when we fill out our charge. Now, there's a couple things. We're going to write parallel rules. We're going to write series rules over here. Now, taking a look at the parallel one, whatever charge comes out of the battery, okay, gets to this point and splits. Some of it goes to the first capacitor, some of it goes to the second capacitor. So Q total equals Q1 plus Q2. You can think of the charge kind of being like the current, okay? And it kind of has a junction rule. When it gets to this junction, some of the charge goes to one, some of the charge goes to the other. But just like in parallel circuits with resistors, the total V is going to equal V1 equals V2, okay, by our loop rule. When I do a loop, I'm either going to go through the left-hand capacitor or I'm going to go through the right-hand. I'm not going to go through both. So whatever voltage I get through the battery, the voltage for the capacitor has to be the same, and I'm only going across one. So the voltage are all going to be equal. And the rule for capacitance in parallel is that the total, you add them up. It's kind of the opposite of what happens with resistors. For resistors, I add them in series. I'm going to do the 1 over rule in parallel. They flip-flop for capacitors. Now, in series, looking at this top one, whatever current comes out of the battery here is all going to get deposited on this plate. So the charges are the same. So Q total equals Q1 equals Q2. Okay? The difference is going to be the voltage. So now, when I do my loop, the voltage in those two capacitors has to add to the total. So V total equals V1 plus V2. And like I said, the rules are reversed. So in series, I use the 1 over rule for capacitors, which is what I use for resistors when I do parallel. So here's our first example. All right, I have these two capacitors in parallel, and the first thing I might do is find the total. So C total for parallel is C1 plus C2. So it's 200 plus 800 is 1,000 nanofarads. Now, I was just doing this problem a moment ago, and I noticed the numbers get really big. So when we make up our chart, leave a lot of space. So QVC this time instead of VI and R. Total 1, 2. Okay. Now we just our first capacitor is 200, our second is 800, and the total is 1,000. Now for the voltage, we have 100 volts in here. For the total, then I use Q equals CV. So it would be 1,000 times 100. It gives me 100,000. Now, since this is in nanofarads and this is in volts, when I multiply them, we get nanocoulombs. I'm doing that so I don't have to worry about the times 10 to the minus 9. Now, looking at this, I have to figure out what I'm going to do next. The charge that comes out of this top here is going to go over, but then it splits. So I don't know what either of these two charges are. I know they have to add to 100,000. Oh, but this is parallel, and in parallel the voltages are the same. So I know this voltage is going to be 100, that voltage is going to be 100. Because whatever loop I take, I'm only going to go through one of the capacitors, so they have to have the same voltage as the battery. Then I do Q equals C times V again, so 200 times 100 is going to give me 20,000. And then 800 times 100 is going to give me 80,000. And those 80,000 plus 20,000 adds up to 100,000. So it works. Now here's a more complex one. I have the 200 and the 800 in parallel, but then I have a 400 in series with it. So again, I'm going to find the equivalent capacitance. I'm going to start with these two in parallel and find out what they're equivalent to, and then that is in series with the 400. So I start out with parallel. For parallel, I add them. So it's 200 plus 800 is 1,000. Then that 1,000 is in series with the 400, so I do the 1 over rule. So 1 over C total is equal to 1 over 1,000 plus 1 over 400. And this doesn't turn out to be pretty. When I do the calculation out, I end up with a total of 285.7. So again, I can do a chart to keep track of things. And again, these numbers don't turn out pretty, so leave yourself a lot of room. All right, so our total voltage was 120. Our capacitors, where there was a 400, a 200, and an 800, gives us a total of 285.7. Then I can do Q equals C times V to get the total charge. So when I multiply those, I get 34,300. I'm going to round to make life easy. Okay, now I have to start thinking about what's going on. So whatever charge comes out of the battery, okay, is going to move over to here, and it's all going to end up on that 400. So now I know the Q for the 400 is also that 34,300. Then I can find the V for that. I do Q divided by C. I get 86 if I'm rounding. So now I know the voltage for this one is 86. Now, I don't know the charge on either of those because that charge of 34,000, maybe it's here, would get split over these two. But if I do my loop rule for voltages, I get 120 when from the battery. So my voltages in any loop have to add up to 120. I have 86 for the 400. And then if I just do the left-hand loop, I would only go through the 200, so that's going to have a difference. So I would do 120 minus 86, and that's going to give me 34 volts. So we're going to say that this is 34 volts for that one. Now it's going to be the same for the 800 because two that are in parallel have to have the same. So I'll get 34 there. Now, if I multiply to get my charge, I get 6,800 for this one. 27,200 for that one. And my check is to add those. If I add those, I get 34,000. And with rounding, that's pretty much the same. Top of the next page, we have one more example. So for this one, now I have these two in series that are then in parallel with the 100. So I'm going to start out with the series rule. Remember, the rules switch from resistors. For resistors in series, I add them, but for capacitors, I do the 1 over rule. My common denominator for that would be 600, so 2 over 600 plus 600 is 3 over 600. So then my C series would be 600 divided by 3, which is 200. Then that's in parallel with the 100, but for parallels I just add them. So my total capacitance is going to be 300. All right, so what do we have so far? We have the 100, we have 300, we have 600, and our total is 300. Our total voltage is 30. So Q equals CV, I can multiply those, and I get 9,000. Now, do I want to use a loop rule or a junction rule? Okay, I think I'm going to use a loop rule. The loop rule is with voltages, and if I go through the loop with this 100, 30 volts for the battery, I have to have 30 for the capacitor. And when I do that loop through the 100, that's the only one I go through. So the voltage for this 100 is 30, right? And then that's going to give me 3,000 here for charge. So I have 9,000 charge comes out of the battery. 3,000 of it ends up on this 100. The rest of it has to end up on this 300. So this is going to be 6,000. And then it's also going to be that on the 600. So this is going to be 6,000. Then I would do 6,000 divided by 300, and that's going to give me E here. And 6,000 divided by 600 is going to give me 10. That's nice because the voltage from here to here then is 20 plus 10, which gives me 30, and that's what the total voltage was there. So that is capacitors and circuits.